Very good. So the first speaker of today is Justin Vines, who will talk about analytic GR methods for the relativistic two-body problem.
Great.
Please.
Thanks,
Okay.
Gabriele.
And we have 3 minutes past the time.
Okay. Yes, thank you very much to all of the participants joining, and especially to the organizers for the chance to speak. So I was asked to talk about analytic GR methods for the relativistic two-body problem. I understood that they really wanted me to focus on traditional GR methods, as opposed to some of the newer approaches to the problem, which have been getting a lot of attention in recent years. And so to keep it simple and hopefully make contact, I will focus on the most traditional approach to the two-body problem and gravitational waves, which is the post-Newtonian approach. That is, basically, we assume that speeds of our system, so we're thinking about binary systems emitting gravitational waves, of course, as throughout most of this conference. Essentially, in the post-Newtonian approximation, we're assuming that the speeds involved are much less than the speed of light, among other things. And we treat a binary system with small speeds and therefore weak fields in a certain way. And one of the main points I want to get across throughout both lectures today and tomorrow is how in this traditional approach, the post-Newtonian field equations, let's say, and let me start with even the Newtonian field equation. Just recall, this is essentially, there's a Newtonian potential that I'll call U, and its Laplacian equals minus 4 pi g times the mass density. So that's, let's say, the Newtonian field equation for gravity. And we know very well that this is representing instantaneous action at a distance. The presence of mass generates gravitational field, but instantaneously at all points in space. So instantaneous action at a distance is this 0th order level, the Newtonian field equation, where we start in the post-Newtonian approximation. And so a first important point I want to emphasize is that such a description using the post-Newtonian field equations, which we'll talk about in much more detail shortly, is only possibly valid in the so-called near zone. And let me get a bit more specific about why. In that, let's say, how big can this near zone be if we're going to describe physics at least being close to instantaneous action at a distance? Well, it has to be the size of the system where we're solving these instantaneous like field equations has to be much less than a wavelength of gravitational waves, let's say. Why? Because we know that retardation affects the finite, the effect of the fact that it takes a finite amount of time for information to propagate at the speed of light, right? We know that becomes important when we get on the order of a gravitational wavelength away from the source. So our description has to be much, this near zone has to be much smaller than a gravitational wavelength. Let's say, thinking about a binary system, the wavelength is, let's say, the speed of light over the frequency, angular frequency. And for a binary, we know, let's say, the velocities involved are related to the orbital frequency. Say, think of a circular orbit. So and let's say the distance between the two bodies is this small r, then we know that the velocities are of the order of r omega. In fact, it's exactly equal to r omega. So coming back down here, this gravitational wavelength can be written as c over v times the orbital separation. And now we see if this radius of the near zone is supposed to be much less than the gravitational wavelength. We see that that's equivalent to, let's say, let me rearrange this a bit. The orbital separation over this r near has to be much greater than, oops, I'm messing this up. Sorry. Right, if we want there to exist a near zone, right, this r near has to be much bigger than the orbital separation. That leads us to the conclusion, sorry, I should have planned this a bit better, that the existence of a near zone is equivalent to, let me just say, I'm getting a bit flustered. If the speeds are small, there will exist a near zone that's much less than the gravitational wavelength. I'll let you work out the last couple steps of algebra. But the important point I wanted to make here was that this description using almost instantaneous action at a distance, it's only valid within this near zone, and we have to switch away from post-Newtonian field equations when we get to the far zone. Let's say, oops, much on the order of a gravitational wavelength away or bigger, we have to switch to post-Minkowskian field equations, which are like, and in fact, we then only need to consider vacuum field equations, but let's say in the linear approximation, we have the wave equation for the metric perturbation. So we can, in fact, describe the propagation of gravitational waves in the far zone. So a lot of what I want to talk about is how we treat a binary, and in fact, that binary could also be traded for a scattering event. As is interesting to a lot of us. We could also describe a scattering event equally well within the post-Newtonian approximation in the near zone, let's say, also using this matching procedure, which I will describe mostly next time, to a post-Minkowskian far zone, right? And so this is to be distinguished from, many people here are familiar with recent applications of the post-Minkowskian approximation to binary dynamics, or at least to scattering events in the near zone. But in this traditional post-Newtonian approach, one still needs the post-Minkowskian field equations in the far zone, but that's matched in the near zone onto a post-Newtonian description. All right, didn't plan that very well, but let me move on to just a bunch of buzzwords for what I want to talk about today and tomorrow. So roughly speaking, today is about conservative dynamics in the near zone, and in particular, how to solve the post-Newtonian field equations. In these lectures, we will just worry about point particle or monopolar sources with world lines, which could represent black holes, or in fact, at the level of approximation we're going to work at, it could be any body. It doesn't matter what kind of body we're talking about. In fact, at the first post-Newtonian level, so that's corrections of order 1 over c squared relative to Newtonian gravity, these equations of motion are universal, and they only depend on the mass of the bodies involved. We can describe these masses as moving along world lines and make sense of that, at least effectively, as sources for the field equations. Talk about equations of motion for these world lines, which can be encoded in a Lagrangian or Hamiltonian. briefly mention things, how these, for example, the Hamiltonian is related to the scattering angle, a story which many of you have heard about. And finally, I think the last thing for today will be multipole moments of the binary system, which are very much important for in this post-Newtonian approach. Once you solve for the conservative dynamics in the near zone, how you relate that, how you convey that information to the far zone and eventually the gravitational waves that are propagating in the far zone is through, in this approach, the multipole moments of the binary system, which are defined by the, essentially the post-Newtonian field. So we'll talk, I hope we'll have time to talk about that in detail today. And then on Thursday, we go to the far zone. We talk about radiative dynamics. And this important process of matching a post-Newtonian near zone to a multipolar post-Minkowskian far zone, following this very well worked out Blanchet-Demour formalism. And talk about the waveforms that would be measured at infinity. Again, throughout the talk, both talks, trying to work through the first post-Minkowskian level to get, the first post-Newtonian level to try to get a feel for the kinds of things that go on also at higher orders. We'll also briefly mention a 1.5 pn tail term in the waveform. Talk about radiated energy and angular momentum, and finally radiation reaction, and in particular the Birk-Thorne potential and its 1 pn corrections. So this is all intended, so this is mostly aimed at our high energy particle physics friends who may not be familiar with how calculations, in particular these post-Newtonian calculations, are done from beginning to end. And of course, finally, wanting to get to a waveform for LIGO. So I'll be trying to give you all the building blocks that are used and some of the concepts to do that. And remembering that this post-Newtonian approach is in fact the most important and in some ways the only way that we have so far to generate waveforms for, I should say, n-spiraling binaries that are seen by LIGO. Of course, apart from numerical relativity, which handles the very end with the merger and ring down, etc. Okay. So having said that, I mentioned I will focus on the post-Newtonian, so we mentioned numerical relativity. We'll focus on the post-Newtonian approximation, but let me mention two very other important analytic approximation schemes for solving the two-body problem in general relativity. So first, each one is based on a certain limit. The first one, Newtonian gravity, you obtain from general relativity essentially by taking the speed of light to infinity. You go all the way in that limit, you get Newtonian gravity. And that's our zeroth order theory, which will treat as exact in this post-Newtonian perturbation scheme. Where, formally we can say our perturbation parameter is 1 over the speed of light. But of course, physically, these dimensionless small parameters, the field strength and the speeds compared to the speed of light are dimensionless small parameters, which we assume are less than 1. And for bound orbits, we know the
Can I make a question here?
Yes, please.
Okay. So there is a kind of people that have claimed that in this case, the force between the two particles in the ultra-relativistic limit, I'm referring to Foucault, for instance, that there is an extra gamma factor. So the masses that enter there is multiplied by a gamma to the cube. Is that correct or is not?
So the mass.
They have also a paper with Blanchet, Foucault, that they look at the n-body gravitational, the n and self-gravitational particles,
Right.
And
so,
their claim is that there is the mass which enters there is not the mass. The rest mass is the mass multiplied by a factor. Gamma, I mean, is the factor of the relativistic,
right.
which tends to infinity.
No, but he's talking about low velocities, not large velocities.
No, but here is C. When we say C going to infinity, it's not V going to infinity.
It's opposite. C goes to infinity.
Sorry.
Velocities.
Sorry. Is there a limit? Do you have something to say about the limit of when V goes to infinity or not?
Well,
V, you mean V goes to C.
Yes,
Yeah.
exactly.
That will be discussed in other talks. I think it should go ahead.
Yeah.
Okay.
I mean, I know what you're getting at. I mean, you kind of want to put a factor of gamma there. Let's say if we wanted to work in the limit where V goes to C, which means gamma goes to infinity, one might have problems with what's going on here. Like if you really wanted to work to arbitrary speeds, all orders in the velocity, is your approximation really valid? If you take into account that it's not just GM over R, but GM gamma over R that should be small. Okay? Right. So that is a very good question. And, oh dear.
I think the next talk will touch on that.
Yeah. Okay, if I may, I'm going to leave that for other talks and focus on small.
Thank you very much. Sorry for that.
No worries. So yeah, after this brief mentioning of this post-Minkowskian approximation, where the idea, as we were just saying, is to try to work to all orders in velocity, but still with weak fields, formally expanding in G. This is an alternative approach, which has seen a lot of recent activity, which I think we will hear a lot more about from Julio in the next talk, which of course is natural for scattering orbits. In fact, to have this kind of scaling, you cannot be bound. As I was saying just before, if you have a bound orbit, then slow velocities implies weak fields and vice versa via the virial theorem for a bound orbit. For scattering, if you want this kind of thing to be true, relativistic velocities but weak fields, you have to be unbound. You have to be in a scattering situation. But as I mentioned before, even though the post-Newtonian approximation is most natural for bound orbits, it also works for scattering in a certain regime. And we will come back to that. Okay, finally, it is possible to work analytically assuming neither slow motion nor weak fields if you assume that in your two-body systems, one of the masses is much smaller than the other. Essentially because if you go all the way in that, so I should have mentioned here, if you go all the way in this limit, G goes to 0, of course, you turn gravity off. And your zeroth order system, which you want to solve exactly now, is very easy. It's just two masses moving on straight lines in flat Minkowski space. Versus to be contrasted with the zeroth order limit here, right, where we take C all the way to infinity, but we still have gravity. We still have Newtonian gravity. And in this post-Newtonian scheme, we treat Newtonian gravity as exact and perturb away from that. That's a big difference between these two schemes, which we will also come back to later in the lectures. Okay, so I was talking about, all right, if you want to work to all orders and velocities and field strength, you can, if one of the masses is much smaller than the other, if you go all the way in that limit, you get test body motion in a stationary background. So let's say specifically Schwarzschild space-time geodesics. That's the limit of the two-body problem, which we get when one of the masses is much smaller than the other. We know how to solve that problem exactly. We have exact Schwarzschild metric, we have exact geodesics and exact Schwarzschild, then we perturb away from that. And that's this, so you could call that the post-test body approximation. This goes by the somewhat funny name of self-force analysis in the community. So let me go straight into, in reverse order, thinking about how we frame this as a perturbation approach. So in this self-force scheme, as we were just saying, you assume that the exact space-time metric is some background metric, which again, it could be exact Schwarzschild or exact Kerr if you had a spinning background. And we're going to treat all of that exactly. The Schwarzschild background, let's say, we treat as exact. And then we have a perturbation, which is caused by the smaller mass. And then, so essentially, this is our ansatz for a solution to Einstein equations. We plug that into Einstein equations, we get a field equation for that metric perturbation. Here I'm just defining the trace reversal of that metric perturbation and a gauge condition, which in this context is often called Lorentz gauge, or it's equivalent to harmonic or denominator coordinates in this context. But we get this field equation, which if you think about it is quite a complicated thing. So this is the covariant derivative on the Schwarzschild background. So we're in this curved background, where we have this curved wave-like operator acting on our field sourced by the little guy. There's also, just this comes out of perturbing Einstein's equations, there's also this Riemann tensor term. Equals some stress energy source. And in particular, this will be some, say, point particle description of the little body. So this is not a very easy field equation to solve, but this enterprise of solving for linear perturbations of a background black hole spacetime due to the presence of a small body that's orbiting, this is this so-called self-force program, which has made a lot of progress in the last 2 or 3 decades. But I think it's safe to say that they're still working on even first order in this approximation scheme, and just starting to breach what happens at second order in this approximation scheme. But again, this is a very important scheme because it allows you access to this strong field and arbitrary speed information. Unfortunately, that's pretty much all I'm going to say about self-force, though I will come back later to already there's even a lot of information just in this 0th order test body limit, like Schwarzschild geodesics. Already the 0th order in that approximation has a wealth of information. Might come back to that. So continuing the post-Minkowskian approach, it's essentially the same as what we just saw, except now our background metric is a flat Minkowski metric. And then we have some perturbation, which formally we say is order G. Let's say the deviation from flat spacetime, and then everything else is actually exactly parallel. Our linearized post-Minkowskian field equation is the flat wave operator acting on metric perturbation is given by our source. And of course, that Riemann term went to 0, and these guys became the flat wave operator. And again, importantly here, as I was mentioning above, these describe the propagation of gravitational waves. And so we will come back to this field equation next time, where we forget the source and just talk about the vacuum post-Minkowskian field equations box H equals 0, and their second post-Minkowskian iterations for describing the propagation of waves in the far zone. Okay, but for all the rest of this talk, we will focus on the post-Newtonian approach. So the analog of this metric expansion for the post-Newtonian, let's say starting with the 0th order level is, okay, first we split space, time into space and time. And this is essential in the Newtonian or post-Newtonian approach. And here, essentially what I've written down is you could say the Newtonian, or you might also call it the 0 post-Newtonian metric, where, so you will recognize here and here, that's the Minkowski metric, but these two pieces are not on equal footing. And this extra piece, all right, let me rephrase this. So the grouping here is more like, this is the 0 PN level. This encodes Newtonian physics, and this you could even call minus 1 PN metric, even though these two parts of the Minkowski metric, U is the Newtonian potential, which we mentioned before. So just for now, take my word that we can make this ansatz for a metric. And we will see that it solves Einstein's equations up to these kinds of corrections if this field equation is solved. This we also already wrote down before. This is the Newtonian field equation telling you that the Laplacian of this Newtonian potential function is equal to minus 4 pi g times the rest mass density, which appears in this way, the time-time component of the stress energy tensor. So in just a moment, I will say more about what is physically going on with this metric and ways to interpret it. But let me first show you how this continues. So we go on and ask, okay, what about perturbation? So let's say first here on this side is the 0 PN metric that we were just looking at. And in fact, and so on the other side are, let's say, the first post-Newtonian corrections. All of them are at order 1 over c squared in this way of writing the metric. And these would be second post-Newtonian corrections, which will drop. So of course we still have the Newtonian potential here. The only new, well, it's kind of generalized in this gravito-electric scalar potential. And the only really new degree of freedom that we have appearing at first post-Newtonian order is a so-called gravitomagnetic vector potential, A, which appears right there. And okay, for where did this come from is a very good question. I'm not going to talk about that, but my favorite reference for understanding where this came from is actually the textbook by Weinberg on gravitation. He has a chapter on the post-Newtonian approximation. And he essentially starts from a more general ansatz for the metric at first post-Newtonian order and shows that by going through, taking the metric ansatz, going through computing Christoffel symbols, computing the Riemann tensor, the Ricci tensor, etc., and then trying to solve Einstein's equations with this kind of ansatz, what comes out is that the metric at the first post-Newtonian order, it can be put into this form, where the only degrees of freedom are this scalar potential and this vector potential. Interestingly, you know, the spatial part of the metric, there's no new degrees of freedom appearing at this level. It's just the scalar potential. Interestingly also, so this is not exactly just the Newtonian potential anymore. It's defined within it. There are 1/c² corrections. But essentially, for example, C. Weinberg, to see why you make this ansatz for the metric, you plug it into the exact Einstein equations and start expanding in 1/c, you will find that Einstein's equation is satisfied plus what we would call 2pn corrections if these field equations are satisfied. We recognize, so remember the Newtonian field equation was that the Laplacian of the scalar potential is proportional to the rest mass density. That's still here. The rest mass density is hiding in there. Now we've added in something that would make this look like a wave equation, the time derivatives in the box operator. But I put it on the other side of the equation because now really this is treated as a perturbation. We don't put, in the post-Newtonian way of thinking, we don't put the spatial derivatives and the time derivatives together to make a box wave operator. We treat this one as our 0th order, and this is a perturbation. We'll come back to this. And then an appropriate source, which includes the rest mass density in there with extra corrections. And the vector potential satisfies also a Poisson type equation. It's Laplacian, spatial, flat Laplacian, is given by some source, which is essentially the momentum density at the Newtonian level, really. Okay, so I was saying, yeah, this is a very good textbook to verify what I just told you, that this essentially, this ansatz for the metric solves Einstein equations if these field equations are solved. That's also discussed here, many other places. Another good reference for especially a lot of what I'm going to be talking about tomorrow is Blanchet's Living Review in Relativity, where actually you can't find even what we were just saying, how to verify that this post-Newtonian metric with these post-Newtonian field equations solved Einstein equations. For that, you have to go somewhere else. But I'm going to try to keep track of the notation here versus in Blanchet's review, especially for tomorrow, and that's what I'm noting there. Okay, so back here I'm just rewriting that same metric all on one line, rewriting the field equations, and now hopefully a little bit more interpretation of what's going on with, as we were saying, the Newtonian physics is essentially here, whereas this guy, you could even call it minus 1pn. And for this interpretation, think about, okay, one of the basic things in general relativity, we learn that if you have a test particle in a background spacetime, it follows geodesic motion. An action that encodes the geodesic equation is essentially just the proper time along the world line. So this world line that we're talking about, so we write the world line as z. It's a function. It could be parameterized in any way, but let's say we're going to give the space-time coordinates as a function of the coordinate time variable in whatever particular coordinate system we're using, t. And then I also frequently use this bold three vector notation. So that's our world line. Its tangent or its covariant velocity would be the derivative of that with respect to proper time. Or again, we could split out a factor of derivative of coordinate time with respect to proper time, and then components in the 3 + 1 split would be the speed of light, and this coordinate velocity here, which would be, so we're trying to make things start to look like Newtonian physics. So our Newtonian physics things are a 3-vector position as a function of time, and then this 3-vector velocity, which is just exactly the coordinate time derivative of that 3-vector position. So the proper time is defined by this equation, essentially. So along with this one, tau will be the proper time if this equation is fulfilled. Plugging this into here with this expression for the metric allows you to solve for this scalar, the derivative coordinate time with respect to proper time, which its inverse is this quantity in square brackets down here. So essentially, I'm just writing out what is this proper time or action for a point particle with this metric. Okay, and we see, so let me switch tools here. So this term here, this pre-Newtonian term, you might call it, yields an irrelevant rest mass contribution. This term here yields this term, which is the Newtonian potential. This term here yields the v squared term. So what we recognize here is the Lagrangian for a particle moving in the Newtonian gravitational field, right? Taking into account the mass out front, this is the kinetic energy, and this is the potential energy. So that's how I'm saying this is how Newtonian physics is encoded in these two parts of this metric. And then all the rest are these post-Newtonian corrections at order 1 over c squared. Okay. So here we introduce this point particle action, which is essentially the proper time, as applying for a test body, but actually to a large extent, this kind of action for a point particle moving on a world line makes sense also for masses whose gravity we're not going to neglect. So for finite, not just test bodies. And in fact, you can come up with, so again, with all of this setup for a world line that we were talking about here, essentially just add this action for the world line, its proper time, to the Einstein-Hilbert action, vary with respect to the metric, and you will get Einstein's equations with a certain stress energy tensor, with a certain source. For the point particle, which is given as follows. So it's often written as in a 4-dimensional way as an integral over the proper time of a 4-dimensional delta function, but here I've already did that integral use coordinate time, and you see that the effective stress energy source for a point particle is essentially just given by its mass times 2 copies of its 4 velocity, and then a delta function along this 3-vector, oh dear. Delta function space along this trajectory, z of tau. Okay. So we can use this as a source for Einstein's equations, at least for our first post-Newtonian version of Einstein's equations. Some people might take a lot of objection to that. I'm pretty sure probably not anyone here. point particles are not supposed to make sense in general relativity. And I will come back if there's time and say something about this, but just bear with me for now. And I think, in fact, probably most people here don't have any problem with this at all. To treat a point particle, to treat a mass as a point particle with a world line and use this kind of distributional source for Einstein's equations. You can, let's just say, it works to a surprising extent. And it definitely works very well at this first post-Newtonian level. So just a reminder, we were talking about, we want to solve Einstein's equations. This is our metric ansatz. Einstein's equations will be solved if these field equations and something I forgot to mention here, this gauge condition, which is the harmonic gauge condition. If these are solved, Einstein's equations will be solved. We want to do that with point particle sources. Okay, so on this page is enough information to fill in all of these components and plug in this source. The source goes here in these field equations. Here on the next page, I'm writing out what you get. So for a single point particle, starting with, so field equations with a point particle source. On this trajectory, with this velocity, first, the equation for the vector potential, which is much simpler. It's just this, it's a Poisson equation, or let's say it's 3 Poisson equations for this 3 vector potential, where the source is, as we were saying, basically, this is the momentum density times minus 4 pi g. The solution is very simple, given over there. It's just the momentum of the particle essentially times g over the distance of the field point from the position of that particle. And so recognize again, this is because, I mean, both the field equation and its solution, of course, are representing instantaneous action at a distance. So at some time, the particle has some position and some velocity. At all points in space, this solution to the field equation just says, okay, it's the momentum of the particle at that time divided by the distance of the field point from the instantaneous position of that particle. Okay, so that one was very easy. You know, essentially, because this vector potential only enters the metric already suppressed by a factor of 1 over c squared, we only have to work essentially to what you could call Newtonian order in solving this field equation. Whereas for the scalar potential, it's a bit more complicated. We have to work including the 1 over c squared corrections in this field equation. So one complication is that it brings in this finite retardation effect, right? We were saying if we put this together with this, that would be our box wave operator, but we're not going to treat it as a wave operator. We're going to treat this term as a perturbation. And then the rest of it, which was our source that we saw here, using this stress energy tensor, turns out to look like this at first post-Newtonian order. That part is essentially easy to solve. I mean, both parts are actually not very difficult to solve. Again, so this looks like instantaneous action at distance. Of course, this is the Newtonian solution. So the Newtonian potential, it's just gm over the distance of the field point from the instantaneous position of the particle. These corrections are just multiplying that, depending on the instantaneous velocity of the particle and a subtle point here. So I'm supposed to be solving for you. So why do I have u left over here? Well, again, in treating everything on the, well, in treating everything except for this as a perturbation on the right-hand side, we can use the solution to the lower order equation of motion and basically plug that in here. If we used the full Newtonian potential here, we would get divergences, right? We want to evaluate this potential at the location of this body. If we included its self field, that would blow up. That's why I've included this external caveat here. So we don't want to include this infinite gravitational self energy, essentially. That roughly gets renormalized into the mass, you could say. But apart from that, that's just the inverse Laplacian applied to this. And then what happens with this retardation term, right, is essentially you plug in the 0th order Newtonian potential solution here, evaluate its second time derivative, and then that's a source for the Poisson equation again. And this is the particular solution that solves that. And that's how we solve the post-Newtonian, the first post-Newtonian field equations with sources. So remember, we're imagining we have some particle with some mass and a world line that goes into source the field equations. This and this are the solutions to those field equations given now as a functional of the world line. Okay, so what's next? We have solved the field equations, but we still haven't said anything about how these, what do these world lines do? How do we get equations of motion for the world lines? Well, we mentioned, of course, above that essentially these world lines should be doing geodesic motion, or an action for these world lines should be given by essentially what we were writing down here, this point particle action. And so you will get the correct equations of motion for these world lines if you vary that point particle action with respect to the world line at given fixed fields. Right? So up here in this world line action, of course, all of these potentials are evaluated at the world line. We don't, if you don't take into account the fact that these potentials are also determined by this world line, at least partially, but treat them as given external potentials, U and A, and then vary with respect to the world line, you will get the correct equations of motion. So those are the correct equations, and they will be equivalent to the geodesic equation in this metric with given external fields. However, right, to some extent, right, or let's say we instead wanted an action principle for a two-body system or an n-body system. You would not get the right equation of motion if you took just this point particle action for one guy, inserted all of these solutions to the field equations for both bodies, let's say, drop the divergent self-energy terms, and then vary that with respect to the world line, you would not get the right equations of motion. Instead, what you have to do, if you think about it, it makes sense that the total action for an n-body system is not just the sum of these point particle world line actions, but also plus the Einstein-Hilbert term. And here I'm writing out the Einstein-Hilbert term through first post-Newtonian order, neglecting boundary terms that are not going to change anything I'm saying about the equations of motion. With our first post-Newtonian metric ansatz, they depend on, of course, our scalar potential and our vector potential. In fact, these terms are both proportional to the field equations. But anyway, what I'm wanting to say here is to get the total action for an in-body system through this procedure of first solving the field equations like we were doing up here, and then we want to insert those field equations solutions, the field solutions, into the action to get an action for the two-body system. We can't forget the Einstein-Hilbert term. We have to add that to all of these guys. But doing that, and then inserting all of the solutions to the field equations, that will give you a correct so-called Fokker action for an in-body system. Okay, so all of the ingredients to do this are in principle here on these two slides, but going through that procedure, taking the point particle actions, adding them to the Einstein-Hilbert actions, specializing to the case of a two-body system, you get this Lagrangian. So this is often called the Einstein-Enfeld-Hoffmann Lagrangian. It was actually not first derived by them in 30. It was actually first derived, or something equivalent was derived by Lorentz and Drost in 1917, but it continues to be called the Einstein-Enfeld-Hoffmann Lagrangian for a two-body system at 1 Pn order. So at order 1 over c squared. This first part we recognize as the Newtonian, the Lagrangian for a Newtonian two-body system, the Kepler problem, and then here are our first post-Newtonian corrections. And right, in using what we said there and using exactly these solutions to the field equations, actually you notice here, if you expand this part of the solution to the field equations out, you will get something. There's two time derivatives. They can hit this world line, which depends on time. So you would, in general, have the acceleration appearing in your solution to the field equations, which would end up in your action. However, at least at first post-Newtonian order, that can be tucked away into a total time derivative that does not affect the equations of motion. And so finally, varying this action with respect to each of the two world lines gives you an equation of motion for that, for each of the two world lines. And importantly, these world lines, Z, are going to be in the same coordinate system that we started with, the same coordinate system in which the metric takes this form, are the coordinates used for these world lines, which are governed by these Euler-Lagrange equations with this Lagrangian. Okay, that's important. Okay, I'm making this comment. If you were not comfortable with point particle sources, it turns out actually the same equations of motion can be derived without resorting to distributional sources by enforcing the second post-Newtonian vacuum field equations outside the bodies. You can derive the first post-Newtonian equations of motion. Since I need to move on, I won't say much more about that, but just in some of the discussions in the past 2 days, it came up, why actually, never mind. I wanted to mention that you don't have to use point particle sources. And in fact, it's an important physical point that how a body moves in a gravitational field when it's at least when it's surrounded by vacuum, right, is to a very large extent determined only by the vacuum gravitational physics surrounding it. And at least at this order, the only important thing about the body, it doesn't matter what kind of body it is, it doesn't matter how you describe it, only its mass, and of course, some notion of its position, a representative world line, matter. And you can derive, in fact, exactly the same equations of motion with much more effort, I should say, but without using distributional sources. Similarly, you can derive the Newtonian equations of motion from the first post-Newtonian vacuum field equations. Okay. Right, so there's our Lagrangian for the two-body system. It's still written in terms of the two world lines, Z1 and Z2. It's often very useful to do a Legendre transformation to go from the Lagrangian to a Hamiltonian, defining canonical momenta in the usual way for a Legendre transformation. Then you get a Hamiltonian, and Hamilton's equations for, again, the positions, trajectories, and now momenta of each of the two bodies. We note that this Lagrangian actually only depended on, well, it didn't only depend on that magnitude R, but it only depended on the vectorial separation between the two world lines. It didn't individually depend on the two world lines. It immediately follows from Hamilton's equations and one line of algebra that the sum of these two canonical momenta is conserved, is a constant in motion. Therefore, we can pick a frame in which that is zero. And that defines the center of momentum frame. And in that frame, the two individual bodies' momenta are equal and opposite. Let's just call that now the new relative canonical momentum. And then we can also easily see that that will be conjugate to this. And we have our Hamiltonian in the center of momentum frame, which I know to many people is a more familiar thing. So here's that Hamiltonian. Now in the center of momentum frame, written in terms on Hamilton's equations, giving us our equations of motion. Again, with the Newtonian part in the first line, the first post-Newtonian part in the second. And I'm using some definitions here, where the capital M is the total mass, mu is the reduced mass, nu is the symmetric mass ratio. And, all right. So we mentioned that at some point it would be nice to have a 5-minute break. Mm-hmm. So let me make that here. So let's take a 5-minute break and come back.
Okay, very good. Yeah, you have still about half an hour then to go. Okay, including questions.
Okay. Now you see.
Good.
So this is called the surface integral method. Because essentially that's how it works. Instead of working in the bulk, let's say where you might have some effective source, or, of course you could also have matter and you could describe it with a perfect fluid or something. But this surface integral method works only in the vacuum outside, and essentially, again, performs surface integrals in vacuum regions surrounding the bodies. Does it break down at some order? I don't know the answer to that question, but I'm pretty sure it has been carried out to derive the third post-Newtonian equations of motion. In fact, I think that was done in a much later paper by Judamase.
I would assume the finite size effects ruin it.
Okay, so yes. There is still, even when you have spin or multipoles or whatever, there is still a way to derive equations of motion for your bodies using the surface integral method. And the thing is, so your body is essentially characterized by the gravitational field outside it. So let's say, you know, and we will get to this shortly, I hope, but in the multipole expansion, in the vacuum region surrounding a body, right, you can read its mass off of the gravitational field. You can also read its spin and its quadrupole moment, etc., from the vacuum gravitational field surrounding it. And that's the whole idea, is like all of the information that's relevant about the body to determine how it moves is encoded in the gravitational field outside it. So of course, you will not get an equation of motion for a quadrupole, for example, because in general, what a body's quadrupole does depends on what kind of body it is. You could be doing all kinds of different things, and that's not constrained by gravity. But how its quadrupole moment influences its motion, that is determined just by really the vacuum field equations being satisfied outside the body. But yeah, that's an excellent question. So in fact, this paper had all multipole moments at first post-Newtonian order on the bodies. They derived equations of motion for bodies with arbitrary multipole moments from this surface integral method. Yeah, very good question. Any other questions? Okay, so if not, we had arrived at this Hamiltonian, which we could say a lot about, but I just briefly want to mention. So this Hamiltonian is, of course, not gauge invariant. This is a familiar fact. It's written in terms of world lines in some coordinates. I could make a change of coordinates and I will have a different Hamiltonian. But I think many people from our amplitudes friends are familiar with the fact that the gauge and the complete gauge invariant information of that Hamiltonian function is contained in the scattering angle function. And if you'll allow me to gloss over the details here, if you have the Hamiltonian, there's a way, so you have the equations of motion, you can solve the equations of motion for a scattering event. Let's say it looks something like this, and both bodies in the center of mass frame are deflected by some scattering angle pi. And that scattering angle can be expressed as a function of the total energy and total orbital angular momentum of the system. Right? The fact that that orbital angular momentum vector is conserved tells us why the motion is confined to a plane, and that in that plane, for a scattering encounter, the only thing that really matters is this angle by which both bodies are scattered. So that function contains the complete gauge invariant information content of this function, which otherwise only has gauge information. So this is, I know, familiar to many of our amplitudes friends, but the point I want to make here is that is not all of the information that we have so far in everything we've been talking about. Importantly, what we constructed above was not just like the final result that we need to go forward. It's not just this Hamiltonian by itself, right? This Hamiltonian, in spite of being gauge dependent, right, in these traditional GR methods, that doesn't bother us so much that it's gauge dependent. In fact, we just pick a gauge that makes life easy for us and go forward and keep track of it. But so what's the extra information I'm saying that's not, this Hamiltonian is not the end of the story of what we've done. It's that this Hamiltonian encodes equations of motion for these world lines. So then we can solve those and then say we have these trajectories. But the extra information that we have is, once we have those trajectories, we then have these solutions to the field equations, right? Once we got these equations of motion for the world lines, we know the world lines. Now we know the gravitational field everywhere in the near zone. So again, the point I want to make is the Hamiltonian, or the equations of motion, or the scattering angle, it's not the end of the story for the conservative dynamics, if you will, in a sense. What we really need to move forward and to relate everything we've done so far to the radiative physics, which is coming tomorrow, is not just the equations of motion for our world lines, but also these solutions to the field equations. Mm-hmm. So these tell us the metric, albeit in a gauge dependent way, everywhere in, at least in this near zone. That's an important point. Okay, I was gonna say something, I might come back to that if there's time. Okay, and now, so first let me talk about the Newtonian field equation. Remember, that was just that the Laplacian of this Newtonian potential is minus 4 pi g times the rest mass density. But then let me drop that source and go to vacuum. So I'm just looking at the Laplace equation. So the Newtonian vacuum field equation, let's say, like we might have our binary here, where in general, you know, rho is not 0, but let's go outside the source. So still in the near zone, but in this vacuum region outside, and ask the question, what is the most general solution to this vacuum field equation? In fact, there are many different ways to write this down, but bear with me for just a moment. Or, okay, actually, let me say, if I first just look up to there, I claim this is the most general solution to the Newtonian field equation, where of course I have to explain a bit the notation. So first of all, there are a set of tensors which depend only on time with an increasing number of indices, which are these so-called mass multipole moments. And we have a mass, so these are tensors with little l indices from A1 to AL. And they here in this general solution are contracted with derivatives of 1 over r. So let me copy that term up here. That was 1 over L factorial minus to the L, and then mass multiple moments contracted into derivatives of 1 over r. So what I mean there is, of course, so there's a mass, expanding out that sum, there's a mass monopole over r. There's the mass dipole contracted into a derivative of 1 over r. But let's say that becomes a 1 over r squared term if n vector is r vector over r. And then there's the mass multiple with 2 indices. So that's the monopole, dipole, and this is the quadrupole. And let me just say it's over r squared. Well, okay, I think I can. 3 ni and j minus, oh, what's going on? Minus delta ij. Anyway, that's just the second derivative of 1 over r. So increasing powers of 1 over r, and then these tensors with more and more indices are multiple moments. And that was one part of it. The second part was another set of tensors contracted with powers of x. And what I mean by that is this, I guess. Eij, xi, xj. Okay. So this, it's a lot of notation to take in, but this capital L is a multi-index, which stands for little l number of indices. When we write this, dl, we mean the a1 up to dal. And similarly for powers of the vector x, where these guys are the mass multipole moments, multipoles. And these guys are the so-called tidal moments. All right. And finally, just to make contact with something that might look somewhat more familiar, this expansion is completely equivalent to an expansion in spherical harmonics. Right? So we were talking about what is the most general solution to the Laplace equation. And it might be somewhat more familiar to some of us that can be written as a sum over spherical harmonics times, let's say, ALM over R to the L plus 1 and BLM over, no, BLM times R to the L. So that might look somewhat more familiar as the most general solution to the Laplace equation. So that's our vacuum Newtonian field equation. And I'm claiming that that is exactly the same as this expansion. So these guys are what we saw here. Right? We had the increasing powers of 1 over r and tensors with more and more indices. Oh, come on. These tensors, the components of these tensors, so this is a vector. It has 3 components. That's L equals 1. So that's the 3 different m values for L equals 1. This L equals 2, the quadrupole, well, you might be familiar with, so for L equals 2, we should have 5 different m values. M equals -2 to 2. How does that correspond with a tensor? Well, this tensor, like all the tensors below, are symmetric and trace-free. So that's why it has 5 components. If it were symmetric, it would have 6 components, a 2-index spatial tensor. If it's trace-free, and by the way, that's what this angle bracket notation means. It means the symmetric trace-free projection of the enclosed indices. Okay, I know this is a bit much if you haven't seen it before, but all right. So these are the terms that are regular at infinity and blow up at the origin. That's these guys. And those are the mass multipole moments. And these guys are regular at the origin, but blow up at infinity. And those are the tidal moments. And the multipole moments characterize the source. So again, we're solving the vacuum, we're thinking about a solution to the vacuum field equations in this vacuum region surrounding our binary. We want the source that's in there to be our entire binary. But in general, it could be immersed in an external universe. And these tidal moments characterize the external universe. So the first one is not important. It actually physically means absolutely nothing. If we had a function of time added, not depending on space in our Newtonian potential. This one, the tidal moment with 1 index, if you think about this kind of term in the Newtonian potential, that's essentially a uniform acceleration. That's the fake gravitational field of you being in an accelerated reference frame. So that one we can also generally get rid of by not being in an accelerated reference frame. This guy is the first important tidal moment. It characterizes the external tidal gravitational field, and it's also symmetric trace-free tensor. Okay. So that's a sloppy, quick introduction to the general solution to the vacuum Newtonian field equation is characterized by these set of, as I was saying, symmetric trace-free mass multipole moments, a set of tensors with this increasing number of indices, the monopole, the dipole, the quadrupole, etc. And these so-called gravido-electric tidal moments. And that's the Newtonian part that we were just looking at before. What changes when you go to first post-Newtonian level? Well, so on the one hand, I'm claiming that what's written down here is the most general solution to the 1pn vacuum field equations, which we wrote down again here. Okay, this part we were basically describing above, but now these things in general will have inside them 1/c² corrections. This part is essentially a particular solution, again, to this expanded retardation part of the wave equation. These parts are mu and nu are gauge moments. So I'm not going to have time to explain this fully today, but let's just say they're pure gauge. But we were writing down the most general solution. Okay, next is this vector potential, right? That was just a scalar potential. Essentially, so this one is somewhat easier in that we don't have to deal with, so it's again, it's actually just 3 copies of the Laplace equation, like we were talking about before. So the general solution is there's going to be some tensors which depend only on time. They're going to be symmetric and trace-free on these, on this multi-index, but now they've got an extra index. And a very important point here is how these tensors are decomposed into their irreducible pieces under SO3. So we've got a tensor that it's not the Z and the Y, they're not, and by the way, so these would be like the gravitomagnetic type moments characterizing the source, and these would be the gravitomagnetic tidal moments characterizing the external universe. But what's very important is how these are decomposed into their irreducible pieces. So when we have one index and then a bunch of other indices, which are STF, the three irreducible pieces are a part which is totally symmetric and trace-free, which it turns out is determined by the time derivative of the mass multipole moments. A part which is anti-symmetric under exchange of I with one of the other indices. That part here determines the new physical current multipole moments. And then there could also be a trace part on that extra index with one of the others. That is pure gauge in a certain sense. Similarly, for the other guys, the totally symmetric and trace-free part is gauge. The anti-symmetric part gives you these gravitomagnetic tidal moments, and the trace part is determined by the time derivative of the gravitoelectric tidal moments. Okay, so this was a bit technical, but I'm very close to the end of my time, but what is the point I'm trying to make here? So we talked before about inside, we had, back up to the original picture. We had this binary system, right? And we wanted to solve the field equations. We did that. In fact, for our point particle system, the relevant solutions to the field equations were a sum of two terms like that, one for each body, and then for our scalar potential, that's the field generated by one body. You just add them together, you've got the total field. And this is what I was saying. This is the important information that we need to move on to talk about radiation, etc., is these solutions to the field equations. And of course, here they're given in terms of these world lines, which are obeying these equations of motion. But the point here is, okay, now I step back from my system. I have my binary inside, but I go in the vacuum region outside it. And what is the important summary of the information in the gravitational field? So my claim is that it is these multipole moments. Right? So I can take those solutions to the field equations that I had before in terms of the world lines, and I can essentially expand them as R is large. And they will automatically, because this is the most general solution to the vacuum field equations, I will find that they have this form with certain values for the multipole moments. The important ones being here. In fact, if I take literally that solution I had before, I will not have any of these tidal moments. I will not have any of these terms that grow as R gets large. I will only have the ones that die off, and those will determine the mass multipole moments and the current multipole moments of my system. And these are the crucial ingredients in going on to talk about radiation and radiation reaction and waveforms using this multipolar post-Minkowskian formalism in the far zone, which is matched onto the post-Newtonian near zone, which we will talk about next time. I think that's the end of my time for today.
Okay, thank you very much, Justin. I think we ate up maybe 5 minutes of discussion time, but certainly there is time for a few questions. Let's see, who wants to intervene? Comments, questions?
Paolo?
Hi, Justin.
Hi, Paolo.
Just a curiosity. So I've heard before, even from you, that in some cases, like for instance, for curved black holes, you have like, you know, these decaying modes and these growing modes, and sometimes it's not possible to separate them. Could you comment on this? Because from what you did right now, it seems like they're very clearly separated into like the external tidal part and the source part.
Yeah, that's a good question. So in what I was doing just now, it was very well separated. And that's thanks to the fact that, an important fact that I forgot to mention here. So this is coming back to our first post-Newtonian field equations are remarkably linear. And it's even more remarkable due to the fact that at first post-Newtonian order, actually, we have non-linearity in the gravitational field. I didn't mention this, I meant to, but we do have a leading non-linearity at first post-Newtonian order, but miraculously with this parametrization of the metric, you get field equations which are linear in the potentials. That's somewhat of a miracle. It happens only at first post-Newtonian order. Okay, but thanks to the fact that the field equations are linear, it's no problem to separate these growing and decaying pieces like we were talking about down here. You know, especially, you know, in the case of like the general solution to the Laplace equation, which is what we were talking about here. Okay, what you were referring to where you do have difficulty sometimes is that was thinking about perturbations of a black hole background. So in doing something like a self-force calculation or to calculate, actually trying to calculate love numbers of black holes is where this kind of question comes up, where you have an exact Schwarzschild or Kerr background and you want to look at linear gravitational perturbations of that. Previously, yeah, there was difficulty in separating external tidal field from internal deformation response. Precisely because at some point in this very nonlinear situation of a black hole background, considering perturbations thereof, it wasn't always clear which parts belonged to the external, in writing down general solutions to these field equations. It wasn't clear how to separate external tidal pieces from internal deformation response pieces. However, some recent works have claimed that that's not really an issue if you consider analytic continuation in essentially the powers. Roughly this index L here, the multipolar order, if you consider it to be an integer, which of course normally it is, in this black hole perturbation setup at higher orders, you encounter these difficulties you're talking about, but they can be solved by analytically continuing to even just non-integer values of L. I don't know if this is answering your question, Paolo.
Yeah, I mean, I think it gives for sure
Yeah.
some background, but so just to repeat, so the problem is the background field. Is that what creates more issues than the case we're studying for non-separability?
Yeah, I'm gonna say yes. I mean, here our background is flat space-time.
Right. But so these issues can happen for Schwarzschild background as well.
Yes. Like you referred to a conversation we once had. I'm pretty sure it was a conversation about computing love numbers of black holes.
Yeah, I mean, that's the usual. Yeah, but thanks for the answer.
Yeah.
Okay, we can go back to it also during the discussion tomorrow. Maybe there is time for one or two more questions, quick ones.
Just a quick question, Justin. So the idea, if I understand correctly, is that eventually one fixes these mass multiples by considering, for instance, a separation of scales between this inner boundary of the annular region you draw, right?
Mm-hmm.
And the outer one, and saying that, for instance, near the inner boundary, the tidal ones will be suppressed and you neglect them. And you thus fix the mass multiples near the inner boundary and vice versa, I guess, for the other ones. Is it correct?
Mostly, or okay, so the mass multiple moments, I should clean this up a little bit. Yeah, they're going to be determined by the source inside, essentially. So they characterize the source, like the binary source inside. And what I was just describing, if we apply this, everything we were just saying, to these solutions to the field equations that we had above, we will not have any tidal terms at all. We will only have these terms that die off at infinity. And they will be uniquely determined by our world line. So the next thing I was going to go through is, what are expressions for these mass multiples in terms of our world lines and their masses. Right? So those are completely fixed by the solutions to the field equations we had before. So maybe part of your question might, why did I even bother talking about these tidal moments if they're zero for the situation that we're thinking about? Well, actually, what we'll come to tomorrow is, yes, we need to consider a post-Newtonian solution in the near zone matched to a post-Minkowskian solution in the far zone. And part of that matching will be determining, let's say, the gravitational waves that are coming out. But also part of that matching will be a consistent matching between this post-Newtonian, post-Minkowskian solution. Kind of tells you, or not kind of, it does also tell you about radiation reaction. And within this setup, like the way, one way of looking at radiation reaction is to say that it enters back into the near zone post-Newtonian system through effective tidal moments from the external universe. So in fact, part of this matching calculation will be determining this tidal moments from the external universe, or this, let's say, that term in the potential will become the so-called radiation reaction potential. So the Birk-Thorne radiation reaction potential is exactly like a tidal moment. So as far as the post-Newtonian interior is concerned, it's something affecting us from the external universe. But it is determined, that effective tidal moment, which accomplishes in the end radiation reaction, in this formalism is determined by this matching again. Is that in the direction?
Yeah, thanks. I guess it will become also clearer next time. Thanks.
Yeah.
Okay, we can continue the discussion also tomorrow. Perhaps it's time to thank Justin for his talk.